Hi, everyone. Thanks so much for coming to this talk. I'm Tabitha Ogilvie. I'm a PhD student at Royal Holloway, University of London, as part of the Information Security Group. And I've just finished an internship between Intel and Intel Labs, which is where I completed this work, which is called Differential Privacy for Free. Where we're going to investigate harnessing the noise in approximate homomorphic encryption. If you have any questions throughout, feel free to unmute or put your questions in the chat. I can't see the chat, but I'm really happy to talk about this. Cool. So here's the plan for the talk. I'm going to start with some motivation. You know, why should we care about this?
Sorry to interrupt. I can't see your screen. I don't know if it's just me.
Ooh. Oh yeah, it just disappeared, didn't it? Sorry about that. I'll start again. Oh, that's very strange. So I'll start again from this slide. The plan for the talk is we're going to start with looking at the motivation. And then I'm assuming there's quite a high level of familiarity with homomorphic encryption in this talk. If not, I'm sure someone in the talk in the chat can answer your questions. But I'm assuming there's probably a slightly lower level of familiarity with differential privacy. So I am going to spend some time talking about what is differential privacy, how do we achieve it? And then I'll give a very brief overview of noise in homomorphic encryption. Then I'll come to the key question. Sorry, I don't know what's happening here. We'll talk about differential privacy for free. And then we'll analyze. We'll present an analysis of, under what conditions homomorphic encryption can give differential privacy for free. Then we'll explore this analysis with a case study, and then we'll conclude, we'll wrap up, and we'll talk about some further work. Okay, so let's start with some motivation. This is kind of an example data science pipeline. It may not look like your data science pipeline, but it is what came up when I Googled data science pipeline and clicked on images. So for someone somewhere, this is what their pipeline looks like. They might acquire some data, then they might clean it up a little bit. Then they might have a data exploration stage where they work out what kind of analytics they want to run. Then they'll have a modeling stage. And then finally, they'll present their findings. And so if we're thinking about how we might introduce privacy or security into this pipeline, because the pipeline exists as is. So, if we really want to improve the privacy of this ecosystem, we kind of need to meet them where they are. There's a lot of technologies at our disposal, and they'll come into play in different parts of the pipeline. So I would say homomorphic encryption, its major use is in this stage. The modeling stage is quite computationally expensive. And so I would say homomorphic encryption is quite a good candidate for injecting privacy here. My apologies if you're using homomorphic encryption as we speak to clean data. But I think in most use cases, this is where it's used. Whereas differential privacy has a lot of utility in the presentation stage. If we want to share the results of our analysis, then differential privacy is one concept we might want to use. Cool. So let's talk about what is differential privacy. So suppose we have a database and we want to run a function on it. Keep it completely agnostic what the function is. Differential privacy is about controlling the ability to tell the difference between two worlds. One world where we ran the function on the database, and in the other world, we run the function on the database, but we change a single entry. So we want to make it so that we can control how much the function output changes if we just change this one entry. We're not in cryptography land. We don't want to completely garble the output. We don't want to make it fully random. We do want some useful analytics or a useful functional output, but we do want to we want to make it so that someone looking on can't just look at the output and go, oh yes, Ben is in that data set. We believe that this corresponds to a useful notion of privacy, because that individual who's there or not there, it's giving them some privacy. It's not the only notion of privacy, but it's one we're going to use, and it's very popular. A lot of data analytics are interested in differential privacy. Cool. So how do we do it? Well, we use noise. Here I've added some Gaussian noise. But if we think about beta, this red line, as being the true function output, so if we ran it with no noise, what would we output? And then we're going to, add a little bit of randomness. So we're going to perturb the output a little bit. And our privacy comes, so suppose the orange line is we've run the function, but on a slightly different database. So this is going to move the true output. And so we're going to add the same amount of randomness. So we're going to be looking at two curves like this. And the idea is that if you see an output, it's not so easy to tell if it's from the blue line or the orange line. Definitely the blue line is higher than the orange line in some places, but it's not impossible on the orange line and very, very probable on the blue line. There's some concepts we need to introduce. I've tried to stay quite light on the algebra, but it can't be avoided in some places. So the ratio between the values at any point logged is called epsilon. It's called the privacy budget or the privacy leakage. How much more likely am I to be in one world versus the other given an output? In the tails, if you look on that right-hand side, you're into a world where the blue line is becoming almost impossible, but the orange line is still probable. So if I see an output in this region, I can probably conclude that I'm on the orange line. And so there's kind of a failure probability. We want to keep this small, and then one of the key notions is the sensitivity. How much is the true function output going to change if we use one database versus another? And maybe intuitively, it's clear that we're going to need to add wider noise the more sensitive the function is. So if the function changes massively with one database versus another, we're going to need to add quite a lot more noise to cover that difference. Cool. Any questions, just let me know. So I've said we're going to add noise to achieve differential privacy, but where are we going to add it? Well, let's zero in on machine learning training. We're going to train a machine learning model. There's a few stages involved in this. We get the data. We set an objective function or a loss function. In a lot of applications, we'll perform gradient updates. And finally, we will kind of output a final model. And to achieve differential privacy, you can add noise at any of these points in the training process. Adding it to the data is probably the least explored in the literature. The objective function, so you perturb the loss function, is pretty well understood, but quite restrictive, the use cases. Gradient updates is very, very popular. This is quite high utility in the deep neural net setting. But we're going to focus on the output. And the rationale is of this. I'll possibly explain when we get to the homomorphic encryption. Cool. Okay, so let's talk about noise analysis. Why is noise analysis necessary in homomorphic encryption? Well, the kind of the class of fully homomorphic encryption schemes we're thinking about are often going to be built on the learning with errors or ring learning with errors problem or some related problem. And that means, the clue's in the name, there's going to be an error or there's going to be a noise. And so noise analysis will be concerned with, problems like, how large is this noise? And when we perform homomorphic operations, if we do a homomorphic multiplication or a key switch, how does that noise change? And why we think about this often is, is that noise small enough to remove during decryption, or is it small enough that we could reduce it during bootstrapping, or is it worth performing a bootstrapping? These are kind of the reasons we think about noise. I don't have time to go through noise analysis now, but I am going to sort of introduce two flavors of noise analysis, two general approaches that are kind of almost colloquially called worst case and average case. And they're going to proceed slightly differently. So in a worst case analysis, here's what you would do. You would bound fresh sources of noise using tail bounds. So for example, encryption, the noise added during encryption is Gaussian. So you would say, well, this can't be more than 6 standard deviations above 0. And then when you've bounded all those fresh sources, you update after each operation according to the worst case growth. So if you're adding 2 ciphertexts, then the noise adds. So you would say, if I know this noise is less than or equal to bound 1, and this one is less than or equal to bound 2, I know the noise after addition is definitely going to be less than or equal to bound 1 plus bound 2. It's very robust doing it like this, as you can imagine. There's no room for error really. You've proceeded according to the worst case. You've taken very, very high tail bounds. And it's also, I would say, relatively easy to implement. Like worst case analyses are kind of, they're implemented in HElib. I'm pretty sure OpenFHE has these in. The downside though, the bounds are quite loose, as you can imagine, like returning to the addition. If bound 1 is very, very unlikely and bound 2 is very, very unlikely, the likelihood that their sum would be bound 1 plus bound 2 is even less likely, right? So you get quite loose bounds. And there's a kind of nuance point here about you get a bound on the noise only. The only output of a worst case analysis is this is how big the noise is, which doesn't normally matter, but it will for this work. Whereas in an average case analysis, the goal is to analyze how the distribution of the noise changes over the course of a circuit. And how we would conclude is, okay, so we get the distribution right at the end of the circuit, and then we use a tail bound to return a final upper bound on the noise. This is the goal. The pros and cons are basically the flip of the worst case pros and cons. So the bounds are tight. They're a lot tighter than in the worst case. You also get a description of the noise distribution. If you don't do this final tail bound, you've got more information. You need quite a lot of assumptions to make an analysis like this work. You need lots of different kinds of independence assumptions, discretization assumptions often, central limit theorem type assumptions. Yeah, and it's maybe a consequence of these assumptions, but maybe other things, that it can be quite difficult to deploy, like programmatically. It would be challenging, I think. Not impossible, but you know, that might not be true for TFHE, but yeah. Yeah. Any questions at this point? Oh, yes. But we're not really interested in bounding noise particularly. We're interested in what this average case analysis gives us, which is a description of the noise distribution. This is going to be key, and this is the feature we're really interested in for this work. Cool. And then hopefully I've done enough to motivate the key research question of this work, which is, can homomorphic encryption noise give differential privacy for free? Can we achieve differential privacy via homomorphic encryption? Can we make the noise inherent to HE correspond to a differential privacy noise? That's the question. Cool. There's reasons why this is not an obvious yes. For example, in most classic schemes, noise is removed during decryption. I mean, in HE, the noise is only there to provide security. So you don't actually want it to be there in your final result. So you'll have mechanisms that mean that during decryption, you can remove it. Linked to this first point, the noise tends to remain small or kind of, yeah, like, so you can remove it, but also because you don't want it to be big in homomorphic encryption, because you don't want it to be there. So is it going to be large enough to provide differential privacy? And then thirdly, this one I've kind of already gotten at, which is you need to know the noise distribution to accurately specify the privacy leakage. Like, if we think about that diagram of the blue normal and the orange normal, you know, we need to know the actual shape of those curves in order to draw the epsilon line. We can't just have a bound. We need to know the full distribution to understand the privacy leakage. So kind of three reasons this might look challenging, but there are contexts in which, you know, these three don't really apply. So in terms of noise being removed during decryption, that's not true for all schemes. It's not true for approximate homomorphic encryption schemes. I'm specifically thinking of CKKS or HEAN, where the authors observed, you know, is it really necessary to keep the strict separation between noise and message? Can we not just treat these noise bits as kind of like floating point errors? And their scheme is really, really high utility as a result of this relaxation. And that means that for our purposes, CKKS or HEAN, the noise is still there in the final result. This has security consequences. That's a little bit orthogonal to what we're talking about today. Noise remains small. Well, if you've worked with CKKS and you've designed a very, very high depth circuit, you might have once decrypted and just seen just garble come out, and because the noise has just started to overtake the correct bits of your message, you know, and then you'd adjust a parameter to make that not true. But that kind of guides our intuition that there probably are circuits for which the noise does not remain small, or we can allow the noise to grow to a point where it's useful to us. In particular, in this work, we're going to explore high depth circuits. And need to know the noise distribution. Well, there's a recent work that that argues that, well, the noise in CKKS is basically normally distributed throughout, particularly after a multiplication. It's still normal. So we're gonna build on the heuristics of this. Yeah. The caveat to this work is, though, that because we don't develop new heuristics in this work, we just use the ones of one, which kind of only looks at the noise after a polynomial evaluation up to a square, and we did not extend that. So we will only be able to evaluate like quadratic polynomials. Cool. So from what I've presented so far, it might seem like we're kind of home and dry. We just need to make sure we meet 3 constraints. We've got to use CKKS because that's approximate. We've got to choose a high depth application. And then we've just got to allow the noise to grow large enough to mask the sensitivity. Seems pretty much like there will be applications for which we can have differential privacy for free. But if you can see my slide count, you'll know it's not quite this easy. For this reason, so just put this on the board with no context. What this is how the variance updates after a multiplication of 2 ciphertexts. You don't need to know what M or the rows are, but this is if you multiply 2 ciphertexts with messages M1 and M2. So this is a little bit obscure, but what we infer is that the shape of the distribution depends on the input data. So we have a normal, but the exact variance of it is going to depend on the database we put in. So like pictorially, if we think back to our original scenario, which was making it bounding how much you could tell whether you were on the blue or the orange curve, before we were looking at something like this, we've just moved the mean. Now we're looking at a situation like this, where we've changed the variance as well as the mean. And this is going to make it harder. We call this message dependent variance for obvious reasons. You can think about this another way. You can think about if you were on the right-hand side, you could look at lots of outputs from this function and you could measure the variance and you could tell which database world you were in by looking at the variance of what you were seeing. And so this message dependent variance is a additional privacy leakage. Cool. Yeah, if you're not a fan of algebra, I've kept it all contained to this slide. So I would look away from this slide if you're not so interested. But we analyze this situation. We've got 2 kind of core quantities: kappa, which is the sensitivity over the standard deviation. And in the standard case, this is a standard result. What you need is your privacy budget has to be greater than square root of a constant times kappa. Constant, the C is dependent on delta. So, you know, in the standard case, it really is just a question of letting the standard deviation grow high enough to versus the sensitivity. But in our case, we don't just need to consider this ratio, but we also need to consider standard deviation 1 over standard deviation 2. So like the ratio of standard deviations in one database versus another. We have 2 results, one in the one-dimensional case and one in the n-dimensional case. We present both because the one-dimensional is tighter. And this is what you get. The C prime is a slightly different constant depending on delta, and it looks like this. So it's larger quite a bit than the standard case. We believe this is tight. One kind of reason we believe it's tight is, and this is a little aside, is so suppose you set tau to be 1. So this corresponds to no message dependence. You're hoping that you're going to recover the standard case, and that what we have here is a generalization of the standard case. And this is what if you substitute in tau as 1, this is what you get, which isn't exactly the same as the standard case, but I think asymptotically it is. Especially when you think about how the constants have changed. So we push our luck to the n-dimensional case. So this is the functional output beta isn't just a point value, but it's a vector, which is what we're going to have in our case study. And it's thornier. You get an extra factor in the square root, and this half t squared minus 1 is now multiplied by n. So it's But again, if you make this tau equal 1 substitution, you do get something that's asymptotically the same as the standard case. So is this tight? I'm not entirely sure, but it's approaching. Cool. Okay. Yeah, algebra over. Right. Okay. So now we're going to explore that result we have with a case study. We've got a lot of requirements on our case study that are going to constrain what we can consider. So it has to be over CKKS. This isn't that restrictive. You can do a lot of things with CKKS. It's got to have arbitrarily high depth. So, or you have to be able to increase the noise somehow. And you have to, at any one time, only be evaluating a quadratic polynomial. This last one is what is very, very constrictive. And the only case study I know of with this property is ridge regression training using gradient descent, which was at WAHAC in 2020. If you know a different case study, please reach out to me. I'd be very interested. Cool. And we're going to look at some graphs now. Yeah. Okay, so I've spared you all the details of almost all of the cryptography, differential privacy, ridge regression parameters, but one parameter that we will have to look at is delta in CKKS. Delta is called the precision parameter. It's sometimes called P in some implementations, and it, roughly speaking, controls the noise. So high delta gives low noise. So this log delta equals 25 is a little on the low side for a standard application. You might be thinking in the 30 to 40 range, but we're prepared to relax delta if it gives us differential privacy. And so this is checking off, these are fully simulated, by the way. We're checking our intuition that we can get variance growth. Like, can we get it so that the variance is growing with iteration? And the answer is yeah. For this case study, at least, not wildly. It's not growing really, really fast, but it is growing. And we had to, normally you only want to bound like a variance above because you're interested in worst case noise. But for this, we're interested in bounding the variance below. So we have to do both. And they're quite similar. Yeah, another key quantity that we have to look at is sensitivity. And you know, how different can the output after K gradient updates look with one database versus another? And we get this kind of shape. This sensitivity is a lot of other quantities depend on sensitivity, so we'll see this shape again. Now I'm kind of, if we hadn't spotted this issue of message dependence, what would our privacy leakage look like? So if we only looked at the variance and the sensitivity and used the standard case result, how would it go? The answer is pretty well. So if we use log delta as 15, then by 50 iterations, our privacy leakage is incredibly small. This would, yeah, definitely fit for purpose. I wouldn't recommend using log delta is 15, but even if we get log delta is 20 or log delta is 25, we get privacy leakage less than 1. Yeah, I think this is deployable. And why do we have the privacy leakage increases with delta? Well, because if we increase delta, the noise falls, and so the privacy leakage is greater. Cool. But we know we're not in that world. We're in a world where we have message dependent variance. So let's have a look at you know, how does the message dependence change with iteration? I've put in that blue line, which is 1, which is like no message dependence. And we get the for log delta is 15. We get very high message dependence at these intermediary iterations, but it starts to fall, but it's still pretty high. But if we increase delta to 20, we get that the message dependence falls massively, which is quite encouraging. And yeah, if we put in 25, you can't really tell the lines apart past iteration 2. Yeah, so this is pretty encouraging, I feel, that if you increase the amount you're controlling the noise, as a consequence, you're controlling the relative noise. So that's, yeah, it's looking pretty good. So then we're going to conclude with kind of our final graph, which is in the full model, how much privacy leakage are we looking at? You can probably already tell from the y-axis here that it's a lot more than in the variance only case. There we were looking only at things less than 1, and I'm going up to 30 now, so it's not looking as good. I've put in this line for epsilon equals 2 because this is kind of what our best case looks like. So just for comparison. Yeah, for the red case, our privacy leakage is quite high, and this is due to very high message dependence. And we find that the message dependence dominates the sensitivity to variance ratio. But yeah, as you increase log delta, because you're decreasing this message dependence, your privacy leakage falls quite a bit. And you know, encouragingly, you can increase log delta to 25, and you're getting this leakage of, yeah, almost 2. So if you increase delta from 20 to 25, you're going to massively increase the quality of your produced model, but with minimal consequence for your privacy leakage. So this is very encouraging. It suggests that we can just keep increasing delta, and because it will drop the message dependence will be good. But that's not true. So I tried log delta as 28, and now at this point the noise is too low, starts creeping up again. The low noise starts to be important again, and so. Yeah, and so, I mean, the question of whether you can get differential privacy for free, I think it really is going to depend on what's an acceptable privacy leakage for your scenario. I mean, epsilon less than 1, I think would be really nice. But in the deep learning literature, epsilons up to 10 are quite standard. So it's really going to depend on your scenario and what your privacy requirements are. Yeah. Cool. So yeah, I'm not sure what time I'm on, but I'm gonna get into the conclusion and further work. So to conclude, what we've done today is investigated the extent to which HE noise can provide differential privacy for free. We identified message dependence as a key barrier to achieving this. We derived new results on the differential privacy in this quite specific setting. We explored our results with a case study, and we found if your privacy budget is roughly 2, then you can achieve this within 50 iterations. For the further work, it's quite a lot to say. I mean, biggest I would say would be further noise analysis. It would be nice to look at different case studies, polynomial evaluations. We didn't use packing in this case study, but yeah, average case analysis that of these scenarios would be great. From heuristic to guarantee, well, I mean, when you're doing an average case analysis just to bound noise for parameter selection, the burden of proof is a little bit lower. You know, it's just for utility. Whereas if you're using this to argue this will be private as a result, you sort of need a slightly a better guarantee. You need to, or at least to understand the effect these heuristics have on differential privacy. Yeah, I've tried to highlight as we've gone like where particular choices were made, where a different one could have been made. Different applications, schemes, TFHE, I imagine, wouldn't have this message dependence issue. Could you design applications with differential privacy in mind to limit message dependence, something like this? We zeroed in on output perturbation because we can make progress there, but that was a choice. Could we look at different kinds of differential privacy perturbation to see how that works? And finally, we looked at differential privacy for free, a kind of buy one privacy enhancing technology, get one for free. All you had to do was relax a parameter. But could we get it at a discount, buy one, get one half price? You have to flood a little bit, but maybe not as much as you would have without the HE noise. This would, I think, be an interesting area to explore. Yeah, thanks so much for listening. Thanks to FHE.org for having me. If you have any questions or thoughts, you can ask me now, or you can email me here. Thanks.
Hi there, thank you for your presentation. I have a question related to differential privacy. I think in general, it's a very interesting idea to use the noise from CKKS, for example, for differential privacy. But my question is, so suppose like I train a ML model over 100 samples. Then I make a DP release.
Yeah.
So after a while, suppose that I add one more sample to my data set, and then I retrain the model and make a second DP release. According to the DP definition, the privacy of that one individual that was added is guaranteed. But my question, if so I make a DP release, and then I add 100 more samples in my data set, and then I retrain the model and make a second DP release. Is the privacy of all those 100 people, say, is guaranteed by our second DP release? So I understand that the privacy of one individual that was added to our data set is guaranteed by a DP release. But if I add 100 individuals to that data set and then retrain the model and make a second DP release, is the privacy guaranteed?
No, I don't think so. This is quite a common criticism of differential privacy, is it is limited to the case where you're swapping out a single entry. So it's quite like almost individualistic in that way. So I wouldn't say so, no. To each individual member of that 100, sure. But if those 100 people were, say, part of a protected group, no, you can't give privacy to them as like, or using these notions, you'd need a slightly different notion, like some kind of N group differential privacy. Does that answer your question?
Yeah, thank you. But this raises a second question, just to be clear for me, because I'm pretty new to differential privacy. If I make, I understand that if I make a second DP release, the privacy is not guaranteed. But if I make 100 DP releases, so I add one more sample to my data set, I make a DP release, I add one sample to my data set, I make a DP release, and so on. Is the privacy of each individual sample guaranteed?
I believe so, yes.
Okay, thank you.
Yeah.
Thank you.
Okay, thank you for the question, and thank you, Tabitha, for the talk. We're going to open up for more questions. I can see there's another one in the chat from Philippe. Philippe, do you want to unmute and ask the question?
Yes, it's just a stupid question. In fact, is the noise introduced by homomorphic encryption sufficiently random for differential privacy? So in terms of determinism, is it good enough?
Yeah, I would say so. That's going to come down to like implementation. Are you talking about like implementation specific choices? Kind of like what kind of RNG is used?
I was just, in fact, having doubt about the randomness of the noise introduced in homomorphic encryption regarding differential privacy. Is it?
I would say so. It's sampled freshly at encryption. There's questions to ask about. Are you thinking for a fixed key generation? Because there are, it's true, times at which you introduce determinism, for example. Like if the keys are generated only once and then you want to train models, like it wouldn't be fair to consider noise that's part of key generation to be random. I think you're right. I do consider it to be fresh for each training. But the determinism, I wouldn't say it's deterministic, no, because you sample like fresh noise for every encryption, and that would correspond to every running of the training algorithm. Does that answer your question?
Yes, okay. Thank you.
Great. Any more questions?
Sure. But thanks, Tabitha, for the presentation, first of all. I think I missed a few minutes of the presentation because of some internet issues, so I really hope that the answer of this question is not in that few minutes.
Okay.
But still, from what I understood, your analysis at the moment is only limited to polynomial evaluation on maximum degree 2. Is that correct?
Yes. So, yeah.
So in case of a neural network, would your work still be applicable for neural networks with square activation functions?
I think it would. I don't know of anyone who's trained a neural network homomorphically. So I'm in the training. Yeah, I know. Yeah. So yeah, I think yes, you could do this kind of analysis for a kind of a toy example neural network, definitely. I mean, but yeah, I think that yeah. Does that answer your question?
Yeah, but I got a bit confused at some point. What do you mean with you're not sure about training? Was your work mainly working on the prediction steps? So
no, I was working on the training.
Okay, good.
Yeah, yeah, but like in my understanding, training limited to decision trees, logistic regression, and linear regression are the trainings that have been achieved homomorphically. Sure. Yeah. Yeah, and in the training, if you have a square activation function, yeah, you're right. Yeah. Yeah, but if you, I think this work would be applicable.
Okay.
To answer your question.
Yeah, thank you very much. Do you foresee in the future to expand your work to polynomials of higher degree?
Yes, with help. Yes. Yeah.
Okay, then thanks again for the presentation and good luck for possible future work.
Thank you so much.
Okay, there's another question in the chat from Riyadh. Riyadh, do you want to unmute and ask the question? If not, yeah, no problem. I can ask it. So the question is, would you please explain the intrinsic relation among privacy leakage, sensitivity, and standard deviation here?
I'm guessing this is not just asking to restate the theorem. Okay, so this is the relationship we have, which is that essentially privacy leakage is roughly like in the standard case, roughly directly proportional to the sensitivity divided by the standard deviation. That is provably kind of the relationship. I can, yeah. So if I'm not going to go all the way back, but yeah, if we want to think a little bit more intuitively, if we think about like telling the difference between these two, if I increased the width of these Gaussians, they would all be flatter, and so the distance between the two lines would be less. So that's why higher width, so higher standard deviation, is going to be smaller privacy leakage. If I move those Gaussians further apart, then the distance between them is going to get higher. So high standard increasing standard deviation decreases leakage. Increasing sensitivity increases leakage. So why it's exactly directly proportional to sensitivity over standard deviation, I don't have a good intuition for you. We repeat the proof in the paper, but I wouldn't say it's the most illuminating. Yeah, I hope that answers your question. Thank you for the question.
Yeah. So any more questions? Lots of questions today, which is great. Any other ones?
Differential privacy is a really cool topic. I think, yeah, if all you take from this is that people in HE should think more about differential privacy, I'm happy. That's,
yeah. Okay, maybe I can ask a question then, maybe a naive question. How does bootstrapping fit into this? Like, does it impact things if you bootstrap midway through the application?
I was wondering about this. I don't know how message dependent bootstrapping noise is. I was wondering about whether bootstrapping noise could be a source of non-message dependent noise that you're looking for. Yes, particularly in the TF-HE case, would be my wondering.
Okay.
Yeah. So how does it fit in? It doesn't fit into the work that's been done. But yeah, I think there's high potential. CKKS bootstrapping, I imagine this is message dependent. Yeah, the noise that you get. But that would be a very, very complicated analysis to do. Not that it shouldn't be done, but yeah, further thought, I think.
Sure. Yeah. No. Thanks for the intuition.
No worries.
Any final questions? Oh, okay. In that case, I think I'm sure I speak for everyone when I say thank you very much, Tabby, for taking the time to give the talk today. It was really interesting, and we it was a pleasure to have you give the talk.
Thanks for having me.
For everyone who's in the chat, if you haven't already joined the community Discord, feel free. I'm going to paste the link into the chat channel now. So we can always follow up there with additional questions, etc. And yeah, thank you everyone for participating today and asking lots of interesting questions. It's been a great meetup. And as usual, all the resources will be uploaded on the website and YouTube within a week or so. So everyone can benefit from today's talk. And yeah, until the next meetup, have a great weekend, everyone, and thank you very much.